Welcome to Unit 10, Acids and Bases, Lecture B. We're going to talk about neutralization and the lab technique called titration today. So acids and bases, remember, acids all have H pluses and bases have OH minuses if we're using the Arrhenius definition. And water is H2O. So in the acid-base unit, a lot of the times you're going to see water written as HOH because this part is from our acid, the H, and then the OH is your base part. So whenever you put an acid and a base together, one of your products will always be water. The remaining ions, so your negative ion from the acid and your positive ion from your base, are going to make another compound, and this is always going to be called salt. Now, salt doesn't always mean NaCl. This is really important. That's the common name we use for table salt. A salt is going to be any ionic compound that's not an acid or a base. So, for example, if we put hydrochloric acid with sodium hydroxide, very common acid to use in lab, very common base to use in lab. The hydrogen from the acid and the hydroxide from the base are going to form your water. And then the leftover sodium and chlorine make our sodium chloride. That's our salt. So you're going to memorize an acid and a base make salt and water. This is one more type of reaction that you're going to be able to identify. So you have synthesis, decomposition, single replacement, double replacement. This one is called neutralization. It is a special kind of double replacement reaction. Acid and a base makes salt and water. You should be able to pick that out. A lot of times they're going to show you just the net ionic equation for every neutralization reaction. Since we're always talking about an acid reacting with a base and it's going to make water, this would be our net ionic equation, and anything else would be extra spectator ions. If you remember in kinetics and equilibrium, we used reference table I. And down here at the very bottom, I had you mark that this was neutralization. So this is the net ionic equation for neutralization. Every time we do neutralization, it is exothermic because we have a negative delta H. So every time you do neutralization, it releases energy. Another example, this is nitric acid. Here's our H+. This is potassium hydroxide. There's our OH-. So this is our acid. This is our base. Water, you should be pretty good at picking out by now, which leaves potassium nitrate as our salt. And keep in mind that salt is a large category of compounds, not just sodium chloride. The lab technique when we do a neutralization reaction is called a titration. And in the back of your reference table on table T, you find the titration equation. I think on your reference table they write it the opposite way. This says Vm equals Vm. Then I think your reference table has Mv equals Mv. It's the same thing. Molarity of your acid times the volume of your acid will equal the molarity of the base times the volume of a base. When we do this neutralization reaction, you need one hydrogen ion to one hydroxide ion. The ratio of hydrogen ions to hydroxide ions is always 1 to 1. So if I use 3 moles of hydrogen ions, I'm going to need to use 3 moles of hydroxide ions, and that lets us use this Mv equals Mv equation. Technically, molarity is in moles per liter, so your volume of your acid, for the units to cancel, would be liters, but since we have volume on both sides, your volume can be any unit as long as it matches. So we've done labs where we've done microscale and we're counting drops. It could be milliliters. Usually we don't use a whole liter of an acid or a base in lab. Titration word problems are very common on the final, so you should make sure you know how to do them. When we read a problem, look for key information. So if 20 milliliters of a 1.0 molar HCl was used to completely neutralize 40 milliliters of a NaOH solution, what is the molarity of the NaOH solution? So 20 milliliters of 1 molar were used to neutralize 40 milliliters of an unknown molarity base. All you have to do is use the MV equals MV equation. 20 times 1 equals 40 times X, and 20 divided by 40 gives me 0.5. The math is very straightforward. The hardest part is going to be reading the questions to make sure you're getting the data. They will make some of these harder by giving you a data table instead of straight numbers. And the piece of lab equipment that we use during a titration is called a burette, and you need to know how to read them, and you need to understand that we're recording how much has been added, not how much is left in the instrument. So they read backwards. If you look carefully at this, you see 40 here, and you see 41 down here. So it's reading backwards because way up at the top would have been 0. We're reading how much we've added. Again, we use the bottom of the meniscus. We're reading this to correct number of sig figs. If we look carefully at the bottom of the meniscus, we would see it's just below the 40. So just below the 40, but not quite to 40.1. So it's going to be 40.05. This instrument, you'll see they're holding a card with a black line on it in the back. When you're reading this in lab, sometimes to be very accurate, you'd bring that black line right up to the bottom of the meniscus so that you can read it. And again, here's 12, and here's 13, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines in between the two. So this is 12.1, 2, 3, 4, 5, 6, a little more than 12.6, so probably 12.68. It's pretty close to 12.7. And again, here's an instrument that has white letters on it. Not having a white card behind it would be better, so they're using a colored piece of paper with the black line. And again, we are somewhere just bigger than, if this is 41, that's 41.1, 41.15. One more reminder that a salt is an ionic compound that is not an acid or a base. So the positive is not H+, the negative is not OH-, and another neutralization reaction to give you yet another example of a salt. So if the positive ion here is H+, this is an acid. If the negative ion in KOH is a hydroxide, this is a base. Water, we're pretty good at picking out. And so the KCl is an ionic compound, not H+, not OH-. This would be considered the salt. Last thing we have in our notes is an example from a Regents exam of what some of these titration problems look like. A student titrates 60 milliliters of HNO3 with a 0.3 molar NaOH solution. Phenolphthalein was used as the indicator. After adding 42.4 milliliters of NaOH, the color change remains for 25 seconds and the student stops the titration. The first question says, what color change does phenolphthalein undergo during this titration? You can memorize some of the indicators, but please remember that you have a reference table for that. So reference table M. We find phenolphthalein. We say here's the color change. At a pH less than 8, it's going to be colorless. At a pH greater than 8 or greater than 9, it's going to be pink. So in our base, it was definitely pink. And when we neutralized it, and it was at a pH approximately of 7, it's going to be colorless. So what color change does the phenolphthalein go under the titration? They want to know the change. So if they're using it as an indicator and they're starting with an acid, it must have started as colorless. And if it's titrated, when it's all done at the end, it's going to turn pink right at the moment when we push the pH up past 7. That's when we know the titration ends. So your answer is going to be from colorless to pink. Show the correct numerical setup for calculating the molarity of the HNO3. Well, we have 60 milliliters of HNO3 and we do not know its molarity. We used 42.2 milliliters of a 0.3 molar NaOH. They just want the correct numerical setup. So you go to table T and see that it's the MV equals MV equation. 60 times X equals 42.2 times 0.3, and then you're done. So pretty straightforward. Just watch your numbers, make sure you match up the correct volume and molarity for the acid on one side of the equation and the two that go together for the base on the other, and then you'll be set. Take the time to underline and look for key information in the questions. That wraps up Lecture B.